Okay, last class, as far as I remember, what we did was look into this, right? And this part we all remember, hopefully. The force diagram bit, that was horizontal circles. We were looking at how tension may um be analyzed by dividing this tension into different components, y and x component. And we're going to find out the net force towards the center and how that relates also to the theta, and how we can combine all of these equations to find this final equation. So we did a bunch of things. We analyzed the tension, we equated it with the weight, and then we finally found an equation that looks somewhat like this. And we also discussed about certain other situations. For example, let's say a guy spinning around. So very interesting example, this one. So someone spinning around some sort of a ball, let's say, stuck to a string, and using their hand to spin it around on a horizontal circle that is parallel to your Earth's surface. So that's an interesting case as well, which has a bit of a limitation, where the limitation is mostly about maintaining a perfect or a constant center position about here, because when you're rotating it with your hand, it's a bit of jitter over there, which is why it's very difficult to perfect perfect horizontal circular motion with uniform speed. But even this you can turn into a question, which I will sort of discuss at some point. If there are more people, I'll probably try and revisit this topic, because this can be turned into a very interesting question. And this has a bit of a nuance to it. And I was thinking about this after someone asked this question, that how can I sort of turn this situation into a question? And I can, if I sort of change a few things about this question. And it's going to be a very interesting question. So once I have a few more people in classroom, I'll discuss that. But regardless, one of the few common type of question that you would see is this one. And this one I gave to you a lot, a bit more as a homework. And I will sort of run through what this question really is. It's same as what you saw above, but with the numbers involved. You're not working just with the variables, you're working with the data given, right? And okay, I'll let a few more people in. Right. So with this question, what you have is an object of mass 5 kg is attached to a string of length 60 centimeter. The other end is fixed to a point O, that is over here. And the object moves in a circle of radius 30 centimeter. Great. So you have this ceiling and this bob, this is the string, and this bob is connected to this ceiling using the string, and the length of that string is 0.6 meters. And there's also this radius of the circle that is through which it's oscillating or going around, and that radius is 0.3 meters. Fair enough. What else do we have? We have the mass, which is 5 kg, and that we can turn into weight. How do we do that? Mg, simple as that. So 5 into 9.8. Now, what is the question? The first question is find the tension in the string. How do you do that? What is the thought process when answering this question? What is the tension? Right. Now, the first thing you start thinking about, what equations do I have already looked into which includes tension? So what is one of those equations? One of them could be this, or it could also be this. These two equations we have sort of um, had a bit of an introduction of when working with this simple, exactly same ceiling horizontal circle motion. Now, when you look at these two equations, which one is easier to work with to find the tension? In both of these cases, you have T. And that is what I want to work with, essentially. That is all I want to work with. I want to find T. I want to make T the subject, and I want to find that. But which one is easier? And I would guess, if I were you, I would take equation 2. Why is that? Well, I do have weight, mg, and tension, I don't know. Well, theta, can I find that out? The cos theta bit? Is that something I can work with? Yes, could. I could. I could work with theta. How, you ask? Well, I do have this length and I do have this length. Can I do something with that? I would assume so. I would assume so. So here's the thing. I have now doing a bit of a deduction chosen. Wait a minute. Okay, so no problem. So yeah, coming back. I have done a bit of a deduction and I figured out equation 2 suits me. And working with that equation, what I need to find out now is I have t cos theta. T cos of theta is equals to mg. Mg I know. T I don't know. I need to find out. Cos theta I have to figure out as well. How do I find out cos theta or just the theta? Let's work with this triangle. I have a simple triangle. And in this case, what you can do is you have zero point 0.6, you have, oh, you don't have zero point 0.6. Wait. This part is wrong. This is zero point 0.6 is 60, yeah, that's correct. So 60 centimeter, if you convert into meters, that's zero point 0.6. Perfect. Zero point 0.6 and 0.3. So now can you use this to find out theta? Is that possible? Now, using this, you can directly find this theta, right? Or you can also find this theta. Mind you, both of these thetas are different. And that is something you need to keep in mind. When you work with this theta over here in the equation, which theta are we talking about? Which theta are we talking about? This one, not this one. Don't make this mistake. Okay, don't make that mistake. So a common mistake would be that you consider this theta to be this cos theta, which is wrong. What you can do is you can find this theta and say, okay, I want to find out the theta that is made with the ceiling. So I say 180 minus this 90 degrees and minus this theta, whatever I find out over there, minus, let's say, theta 1. Now this gives you, let's say, the theta made with the ceiling. So now you can, equate this theta into this equation. That's something you can do, or you can also do something simple. You can just, you forget about whatever theta is given in the diagram. You just, make your own triangle and you say, okay, I'll name this theta, let's say theta C. And I say, what equation can I use? What equation can I use? Which trig formula comes to your mind? Anyone? If I want to find out the theta C. No one? So I have the hypotenuse and I have the opposite. You can just text me or something. I don't know. I didn't open up Slido.
Fine.
Yes, sine. So exactly. So you can use sine is equals to opposite, which is 0.3 divided by 0.6. You get the theta, which is theta C. Right? Once you work with that, you have theta. That is this one. So you find t cos of theta C and mg. Can you now find out tension? Yes, you can. So that is one way to find out the tension, right? That's an easy way to find out the tension. So if you do that, you will find out that tension is equals to what did I write over here? 56.63, right? If you guys go through the calculation and it matches with the answer, great. Okay, so that's one of the easier part of this question. And I mean, this is sort of how the questions are going to be. You're going to be given some numbers. Just have to find out which equation is suitable and then move on with that equation to solve the question. Fair enough. So is this part sort of easy to understand? Do we get what's happening over here? What am I doing? Yeah. Thumbs up, thumbs down. Mm-hmm. Okay. Okay. Any confusion if you guys have, do let me know. I'll repeat it. I'll move on to today's part, which is vertical circular motion. But before that, I just want to make sure this problem solving part is doable for all of you. Okay, so that's one part. If you guys don't get the answer, do let me know as well. Now, what's the other part? Angular speed. Angular speed is what? Omega, right? So at what rate is the angle changing? Rate of change of angle. For that, what can we do? We can we can work either with v is equals to r omega, or I can say, well, no, I want to directly work with, let's say, the centripetal force formula, which is going to be, do we know the centripetal force formula? One is mv squared by r, the other is, let's say, mr omega square. So these are the two formulas we are known to. Now, exactly this I can be working with. Now, again, I have to relate back to my equations over here, right? So, is this something we can work with? Tan theta is equals to v squared by rg. Can we work with this idea? Right? This is one of the equation we figured out last class. Can I work with this idea? Yes, probably we could. Why not? We know theta. Do we not know theta? We found out theta. Tan of theta, just use the calculator. Velocity. Now, velocity is not something you would know of, but can I substitute something into velocity? Is there something I can substitute into velocity? Yes. If you remember the equation of velocity, v is equals to r omega, right? This, remember, I just wrote down over here, right? So that you can substitute. This v is equals to r omega, you can substitute and say, okay, fair enough. Tan theta is equals to r omega whole square divided by rg. Can I further simplify this? Yeah, sure. Why not? Divide by r omega square by g. Now, do we have everything we want? Do we? Yeah. Theta we know. Radius of the circle I know, which is zero point 0.3. Gravity I know. And angular speed is exactly what I want to figure out, right? So you can now just substitute all the relevant data that is given in the question, make omega the subject, and you get your final answer, which is going to be 4.34. Now, probably over here, what I've done is a bit of a different path, but I've just explained to you what is an easier way to do it. Or a more relevant way to do it using the previous formulas. Even in this case, I have used the same idea. It's just that I probably just skipped a few steps, which may be a bit harder to understand if you just look at with accounts. Anyways, hopefully these two questions we all understand to an extent. One is tension, right? One is tension where we simply equate it to mg. We took help from this equation, equation 2, right? We found theta first. So first job was finding theta, equate to this equation, and then we found out tension. That was one. And the second question, angular speed, what did we do? We simply used this final formula, which is with respect to tan theta. So this one, very simple again. We substituted v is equals to r omega for this so that we don't have to work with velocity. We don't want to work with velocity because we don't even know what the tangential velocity is. So granted, we have removed velocity from the equation. Now we know theta, we know r, we know g, and we have omega into the equation, and now we just make omega the subject. Okay, fair enough. So hopefully till this point, we don't have much of any question or confusion. Are we on page till now? Yeah, I'm hoping. No questions? No questions? Great. Give me a moment. I'll just open up the Slido. We are going to start off with this. You can take a look of what this is or take a screenshot if you wish. Uh, Okay, I can't really use. Yeah, I won't be able to use Slido today. Never mind. Coming back to this. So this one, as mentioned in last class, is going to be a bit more complicated as comparison to horizontal circular motion. Now, if you guys have a good enough concept of horizontal circular motion, where the only difference is um, horizontal circular motion is a uniform circular motion. What does that mean? Velocity remains constant. Horizontal circular motion, my velocity remains constant. Okay. What else remains constant? My centripetal force, Fc, remains constant. And in case of vertical circular motion, it's a bit different. What happens? My velocity, tangential velocity, keeps changing throughout the journey. And as a result, my centripetal force also keeps changing. And if you want to know why does my centripetal force change, look at this equation. Fc is equals to mv squared by r. What do we have in this equation? Velocity, right? So if my velocity is changing, isn't it also true or obvious that my centripetal force must also change? So that is exactly what's happening, right? So as a result of the velocity changing, we have our centripetal force changing as well. Okay. And why does centripetal force change or velocity change? Like, what's the reason behind both of those changing? It's mostly because the way the object travels through the circular path and how the force changes its direction. So if I have someone, a man or a woman over here, right? So this is the bob, and it's in vertical circular motion. So this motion is perpendicular or normal to the Earth's surface, right? And in this case, what's happening is, granted there's a string over here, the tension is always inwards, right? The tension is always inward towards the center. Now, when the bob is up there in the topmost position, what's happening? The tension is pulling the object or the bob downwards. If I, say this direction is down and I say this direction is up, then with respect to that, when the ball is up in the upmost position, the tension is pulling it downwards. And when the same ball, it goes around and comes back to this lowest position, the tension is pulling it upwards, right? So see how the direction of the tension has changed. Now, all while that is happening, my mg is always pointing downwards. Is that not the case? So while tension is changing its direction, my mg does not change. And this difference or this constant change in direction of my tension is causing the main problem. This is why we have a changing velocity or a changing centripetal force through the journey. This is the problem. This is why vertical circular motion gets a bit more complicated. And let's look into that through in-depth analysis. Now, I mean, hopefully you understand what this diagram is. If not, if you look carefully, this is simply the red dots are simply the position of the bob, or a ball, piece of ball, let's say. And it's going through vertical circular motion, right? So this, if you look at the key over here, it's a yo-yo, it's a ball, whatever you want to say. And that piece of object is going to vertical circular motion, and the four position labeled as 1, 2, 3, and 4. And we will mainly be analyzing position 1, and position 2. Okay, let's see what's happening. And these two position position 3. Yeah, position 1 and 3. And these two positions are very important and very special to give us insight into how vertical circular motion really happens and how the forces change and what we can say about the tension, how the tension varies through the circular motion. And we will be able to form a bunch of equations out of this, exactly the way we did for horizontal circular motion. We always want to make sure whatever we're looking at, can we justify it using equation? That's the main physics. That's where the math is. That's what we want to do, right? So we want to do the analysis of the force and we want to form equations. And we want to make a few conclusions. First thing, when analyzing the position 1, what do we see? The tension by the string and the weight of the ball itself is downwards, right? It's in the same direction. And when you are in position 3, while the weight is downwards, the tension is upwards. Now that's a bit of a difference. Now, to add perspective to this, when I sort of give you a bit of a real life demonstration, take a piece of ball, attach it to a string, and try and rotate it around in a vertical circular motion, and do it at such a speed that you can understand the variation of the speed. What you will realize if you have the physical intuition of what's happening is at the lowest position, you feel that the ball is providing or pulling your hand a bit too much or in a much stronger manner. And when it's in the topmost position, you feel like the ball might just fall down. The tension in the rope feels less. It feels like the ball might just fall down if I don't rotate it with enough speed. Why is there such a difference? And the biggest reason is when you're at the topmost position, if the tension and mg both is pulling the bob downward, isn't the string going to get slack very easily? Because this is the string, and if both tension and your weight is pulling the bob downward, then the string has a greater probability or a greater chance of being loose or having zero tension. Having zero tension. Why? Because both tension and mg is downwards, right? Your centripetal force is downwards towards the center. So it's going to fall down. That is where the problem is. And that is what we analyze to understand what is the minimum velocity we need for the circular motion to be maintained. So you will often hear this. You will often hear this that all those experiments that you see with someone having a cup of, let's say, glass of water and attaching it to a string and saying, okay, I'll rotate it around, and if I rotate it with the right speed, the water inside will not spill out. When they say the right speed, what they essentially mean is the speed should exceed a certain amount. The speed, what am I writing? The speed should be greater than a certain amount. Why is that? And how do we find that? We find that by analyzing this position because this is our weakest link. This is where the problem lies. This is the position where we can have the string going slack. Again, why can that happen? Because both the forces are pulling it downward. This is where the string can get slack. Not over here. Not over here. Because you have, even without any speed, without zero speed, if you just keep a ball hanging through a string attached to your hand, it will just stay there. The string is never getting slack. The ball is pulling it downwards. There will always be tension. There will always be tension. Yeah. It's someone asking something.
Explain that part again.
Sorry, I can't really hear you.
Could you explain that part again?
Which one?
The why there is the tension here is minimum.
The topmost position, this
Yeah.
one?
Right.
Yeah, so the tension over here is going to be minimum, and I'm going to prove that with the equations as well. But I'm just giving you an intuition of the idea. Is look, the mg is pulling it downward, and if there is tension, the tension will also pull it downward. So the ball has a tendency to fall at the topmost position. And if I have a ball and a string over here, and the ball wants to fall down, wouldn't this string go slack? Slack basically means zero tension.
Yes.
So if that is the position where I have the net force acting downward, right? I have all the forces acting downward. That just means that is my weakest link. If if my circular motion is supposed to be broken at any position, position one is the place
All
because
right.
both the tension and mg is pointing downwards. And if both are pointing downwards, greater chance that the string goes slack. Are you getting my point?
Yes.
Right? So if there was a force upwards, then that would make the string tight, right? Okay. So that's just giving you guys a bit of a physical intuition of what's happening. You will obviously understand entirely and with a eureka moment when you see it with the formula. That's where it will all make sense with the equation proof, with the derivation. So now, hopefully, you know what's happening with position one and what's happening with position two. Now, let's see with maths what's happening, right? Taking position one over here, what do we have? Let's just determine something. I'm going to say downwards is positive and upwards is negative. The reason I'm doing that is ease of math and ease of sign change. You can consider any side as anything. You can say upward is positive and downward as negative, doesn't really matter. But whichever convention you choose, you have to go through with the entire derivation or entire maths. Okay, I'm just choosing this for ease of proving something. So I have a bob, and at position one, what I have is both mg and tension pulling it downward. Hence, my net force is also downward towards the center. Oh, now, by the way, the net force is the centripetal force, right? The net force is going to be the centripetal force. Now, for position one, what we have is F net is going to be given by the sum of mg and T1, which is tension. Tension in position one, I'm calling T1. And do you understand why this equation makes sense? The reason being, the net force is going to be the resultant force of all the forces acting on any object. So what are all the forces on my body over here? A, there is a tension inwards, that is downward, and there's mg, weight, acting downward. Two forces. That's it. That's it. And if there are those two forces, let's sum them up and see where it points. And it points towards the center again, because both are in the same direction. So that is my F net. That is my what? F net. Centripetal force, let's say, right? Not just let's say, but it is centripetal force. That is my net force. T1 plus mg. There is no other force acting over here. No other force. No friction. I'm telling you guys, we're not considering friction over here. So no other force. And if you can think of any other force, let me know. Let me know. Right? So in position one, we have determined there is T1 acting downward, mg acting downward. Hence, sum them up. My net force, my centripetal force is going to be mg plus T1. Great. Now, if I analyze position three over here, what do I have? Again, same convention, upward. Okay, we have used a different convention over here. Again, for the ease of the signs. So I'm taking upward as positive over here and downward as negative, because it looks good. That's why in both cases, it just written in a way that looks good without negative sign. That's why we took the sign convention as it is, right? No other reason. There's no other special reason. You can take anything. It won't be wrong. I'm telling you guys. Anyways, so basically when you have this position, position 3, what's happening is your mg is downward, right? And your tension is upward. So this is where the difference is. Both are acting the opposite direction. Can you guys see my screen? My internet just went off. That's a bit of a. Can you guys see everything? Yeah. Okay. Let me know if at any point you guys can't see something. I don't know when the internet is going to be back. I'm just using data over here. So sorry about that. Hopefully the meeting is getting recorded. If not, that's going to be pretty sad. Anyways, where was I? So over here at the lowest position where you have position 3. Now both are in opposite direction, right? So this is where the interesting thing comes into play. And when I form the equation right now, with respect to the different signs, with respect to, wait. Okay, so with respect to the different sign, now when I say, okay, let's find the F net or the net force acting on the bob, F net now is going to be T2, which is tension 2. I mean, I should have written it as tension 3 because it's position 3, but don't get confused. I'm just writing it as T2. So T2 is acting upward. T2 is acting upward, which is going to be positive, minus, minus what? Minus my weight, which is downwards, and which is negative. Why? This I've given downwards to be negative. That's why minus mg. Now, even without the sign convention, you can just go by the idea of opposite sides. So you can just say, yeah, sure, if I have both in the same direction, the net force in the same direction, so everything is positive, I don't need this sign convention. Sure enough, you can do that. And in this case, you have both in the opposite direction. So if net force is in this direction, then that just means F net would be equals to T2 minus mg anyways. I don't really need this sign convention. But when you work with, more complicated cases, it's always good and always easier to work with a sign convention. That makes working with the formula a bit easier because you don't make these mistakes. For example, one can, go ahead and I mean, in this case, you wouldn't make that mistake because it's easily understandable that both are in the opposite direction. But one could just say T2 plus mg because their sign convention is a bit mixed up. So that's where mistakes can come into play. Anyways, you would find it relevant when working with multiple forces acting together. So in this case, what we have essentially understood is we have established two equations. One is where we have my net force being equal to the sum of mg and tension. The other where it's a difference. Now, can you already sort of understand why my centripetal force is supposed to be different throughout the journey? Isn't it clear to an extent? One, I have the sum of two forces, the other, its difference. So as the position changes, the way the forces are acting, they're also changing. The directions are changing. So that is the interesting bit about this. The direction of forces change, which is why this complication comes in. And based off these two sort of equations, I can say something. That is, in position one, in position one, my tension is less than in position three. And for you to register that better, I'm going to do something. I'm going to make tension over here the subject, my position one. Let's see what happens. mv squared by r minus mg. And what happens in position three? My T2 is, or tension is simply mv squared by r plus mg. Okay. Now, can you guys tell me what's the difference? Over here, when I'm working with tension at position one, it's the difference between centripetal force and the weight. And in position three, it's the sum of centripetal force and mg. So this is the proof by the equation that tension will indeed be greater at the lowest position. And you guys, before getting into all these math, I was giving you guys a bit of a physical intuition. I was telling you guys, tie a knot to a ball and drop it below and try holding it with your hand, and it will just remain there. The string is never getting slack. Tension will always remain there, right? If you have a string attached to a ball from the ceiling, this string is never getting slack. This mg over here, hence the tension will also equal to mg. There's nothing happening over there. String will never get slack, right? So the lowest position, you have zero risk of the string getting slack. Where you have the problem is this upmost position. That's where the problem is. Why? Because of how the equation is. See, if you understand the equations over here, half the job is done, right? So what are my observations? Again, let's go. My tension at position three, or the lowest position, will always be greater. And to find the minimum speed for which we need the circular motion to be carried on, the minimum speed at which it makes sure that circular motion, vertical circular motion, is carried on, is going to be found out by analyzing this position. Why? I've already explained it numerous times. Yeah, I've already explained it that over here, this is where the string can get slack. So if you don't have the highest or the accurate, the minimum amount of speed over there, the string is getting slack. The string is definitely getting slack. Again, to prove it by equation, for the tension to be there, what needs to be true? What needs to be true? My velocity should be more. For the tension to be greater than zero or positive, you want to make sure this is never negative. This entire right hand side should never be negative. Never. And for that to happen, since I have a negative sign in front of mg, what needs to be increased? What is a variable over here? Velocity. That's why, my friend, people keep saying a minimum velocity in case of vertical circular motion. Because the only variable over here is velocity. What can you change? Velocity. What can you increase? Velocity. What will you increase to maintain the circular motion? Velocity. Okay. So this is the proof. This is the mathematical proof that, to find the minimum velocity, what do we analyze? Position one. Where can the string get slack? Position one. That's it, right? So last thing, and for the max speed, is there anything called max speed? Well, technically, sure. If, let's say, what happens if I increase the speed? If I increase the speed over here, um, then the tension keeps increasing, right? And in case of this equation, again, if I keep increasing the velocity, the tension again keeps increasing. And this one, at this position, the tension increases way more than this position, right? At the topmost position, because tension is already little over there, less than the position three. So when I keep increasing the velocity, you know what happens? The tension is so high that the string can sort of break off. So it is about the material of the string that can cause for there to be a maximum velocity. So it is the incapability of the string to withhold the tension, which may cause for there to be a maximum speed. Okay. So if the string is a weak string, then yes, there can be a notion of what is the maximum speed. But otherwise, if you have a really, really strong string, it doesn't really matter. It doesn't really matter. You can have any amount of speed, right? There's no maximum speed in that case. So is this bit clear? And there can be questions regarding this, but I have personally not seen many till this point. Forget many, I haven't really seen any till this point, coming with this amount of conceptual depth. But yes, any question till this point with this? Are we confused about any part over here? No? Are we clear on this part? Vertical circle? Hmm? Okay. Okay. Great. So if that's the case, I would love to break your brain a bit more with this topic and get into a bit of a derivation. Is this necessary? No, that's why it's called further physics and derivation. But I just want to pull it out with you guys. Okay, what's the time? Okay. Last is contact forces. That's going to be an important part. Now, for this same case, same vertical motion, let's do something else. I have analyzed position 1, I have analyzed position 3. These two I have done. But what about positions which are not the extremes? So, not the topmost position and also not the lowest position. Let's take somewhere over here. Let's take somewhere over there. Now, can I analyze this position and make some judgment? Let's do that. Let's do that. So, if I'm going to, so I'm just calling this as expressions for the tension in varying position. So, I'm just taking a random position over here. Let's do something. And I'm going to say, what is the net force for this object, that green object? The net force is going to be T5 tension. I'm just calling it T5, nothing else, which is pointing towards the center. So that minus my mg cos theta, not mg, not mg. Why? Because if this is my center, this is my string, this is my object, the mg acts downward. The mg does what? Acts downward. But what I really need to find out over here is what is the net force towards the center? That is F net, right? So if I need to find out the net force, I also need to find out what is the force exactly opposite to my center. So if this is my direction of net force or centripetal force, what force do I have exactly opposite to that to make sure I have included it in the equation or I have cancelled it out from the tension? So if this is my T5, I have to know what force do I have exactly opposite in the direction so that I cancel it off or subtract it from my tension. So what is this opposite direction, my friend? What is this force in this direction? It is going to be, if this is my theta, it is going to be mg cos of theta. Are we clear on that? So it's simply that mg has two components, one in this direction along the circle path, so along this path, right? So mg has two um, components, one along this path, and the other is going to be over here. So this is going to be mg sine of theta, right? That is, let's say, the vertical component, and the horizontal component over here is mg cos of theta. So there are two components, and the one I am interested in is mg cos of theta, because that allows me to find out the net force towards the center or the centripetal force. So that I want to find out. And in doing so, what I see is my net force or the centripetal force comes out to be T5 minus mg cos of theta. Great. Now what can I do? Now I want to analyze the tension. So I'll make tension the subject. What will I do? I'll make tension the subject. T5. I've made it the subject, and I've said T5 is equals to F net, or the centripetal force, plus mg cos of theta. Great. We are all on page till this point. And all I'm doing the next step is turning the F net into its equation. What is that? Your FC, centripetal force, is simply mv squared by r. We have gone through this so many times, you should have it memorized, inscribed in your brain by now. Okay, very important equation. So now if we have this equation, let's do a few things. Let's analyze when, based off of this equation, do you think tension will be max? When do you think tension will be max? Now, what can change over here? What can change over here? Velocity can change. Can mass change? No, mass is constant. Can radius change? No. If it's, proper vertical circular motion, radius will always remain same. It's a circle, my friend. It's not going to change. So mass stays the same, radius stays same. My gravity also stays same, of course. Nothing is happening to gravity, right? Earth is not changing its mass. So nothing happens to gravity. There's that. What else can change? Theta can change. Now, why am I interested in theta? The reason I'm interested in theta is because that relates to the position. And this further physics bit, all I'm doing is I'm sort of reinforcing this, all of this that I just explained for so long, but in a different way. I'm using a bit of a derivation over here to prove this same thing to you guys in a bit of a different way. So if you just pay attention over here, I'm going to play with the theta to prove the same thing to you guys. So notice, I can change one thing over here other than the velocity, and that is my theta, which denotes the position of the bob. How, you ask? In this position, what is theta? 0. 0, right? If I increase from this position and the bob goes to over here, and this is my direction of mg, and this is the horizontal component of mg, did the theta increase? From 0 to this point, did the theta increase? Notice over here, did the theta increase? Yes. Now, if I change the position again, yet again, to this position, has theta increased? Notice this part. Yes. Now, if I increase to this part, what's happening? Let's see. mg is in this direction, which I have already denoted, and there is no horizontal component of this mg. So in this path, in this direction, the component, or mg cos of theta, is actually 0, because cos 90 is 0. So theta over here is 90 degrees. Theta over here is 90 degrees. That basically, we're interested in theta, but I'm just telling you guys, mg cos theta is 0. Why? Because if you remember the cos theta curve, if this is your 180, this is 90 degree, and this is where, cos of theta is 0. So just to prove to you guys over there, your horizontal, there's 0 horizontal component over there, right? So anyways, my point is, what I want to prove to you guys, what I want to show to you guys is, as you increase the position, as you change the position, what's happening? The theta is changing, right? The theta is increasing. Now again, same thing. This position, theta has increased. And again, this position, theta has increased to what? 180 degrees. So that is what I'm interested in. That is exactly what I'm interested in. And that is the exact thing I want to work with. So by changing the theta, what am I saying? What is the position of the bob? Okay, what is the position of the bob? So now, if I have this equation and I say, okay, when is tension max? When I have, if I keep my velocity same, if cos theta over here is 1, then and only then is my tension max. And you may get confused about that. Why? Because cos theta can only vary between, if you've done maths properly, you will know cos theta can only vary between -1 and 1. So what is the max value, even if with changing theta, whatever I change it to, what is the max value that I can get for cos theta? 1. So that is the value I'm going to take. I want the cos theta to be 1. Because mind you, again, other than theta, I can't really change anything. I can change velocity, but I'm not, because I'm interested in the position. So with respect to changing position, how does tension change? That is what we are figuring out. That is what we are figuring out. So for the max tension, what should cos theta be? 1. And for cos theta to be 1, what should the theta be? 0. Again, coming back to the cos theta curve. When is cos theta 1? When is cos theta 1? Theta is equals to 0. Or theta is equals to 360, which is the same thing. Same thing. Okay? So theta is 0, cos theta is 1. And that is exactly when tension is max. Isn't that the exact same thing that I taught you guys over here? Where? Right over here. So I told you guys that at the lowest position, tension is supposed to be max. Why? There you go, the derivation. So this is how, by analyzing the theta, you can prove to anyone that yes, at the lowest position, tension is supposed to be max. And I can also prove to you guys the opposite thing. That is, when is tension minimum? What do we need for the tension to be minimum? If you have already got the hang of it, you would say, since cos theta can change between only 1 and -1, then cos theta must be -1 for tension to be minimum, right? And you're right. And you're right. My cos theta should be -1. So when is cos theta -1? When theta is 180 degrees. Okay? So when theta is 180 degrees, it is only then cos theta will be -1. And if that is the case, my tension is also minimum. So now, if you look into the equation, theta is 180 degrees, right? So cos theta is -1. So ultimately, what do you get? mv square by r minus of mg, because cos theta is -1. So there you go, that whenever you have a situation, what just happened? So yeah, whenever you have a situation where you're coming back to this position, your tension is going to be the exact minimum. Can you guys see my screen? Someone can't see my screen, so I'm a bit confused.
Yeah, I can see.
You can see? Okay. If in the case you can't see my screen, you can sort of exit and rejoin. I'm not sure if it's a problem on my end. I can stop sharing and reshare again. That's something I can do. But if you just rejoin, I guess you'll be able to see the screen. You should be able to see the screen. If anyone else has the problem with seeing the screen, do let me know. Okay. So till now, what we have talked about is, yeah, okay. So till now, what we have talked about is using this entire bit of math. I just showed to you guys and reinforced the same idea. Same thing, taught you guys again using derivation. Very simple. And this is something you guys should get used to. This is how math works to prove things,
Okay,
right?
sir.
Okay. Yeah.
So I would like to ask. So in point number 3, we
Yes.
say that over there there's the maximum tension, right?
Yeah. Yeah.
And at number 1 there's minimum tension.
Yes.
So I went through a question that said So explain what happens for in this case if it goes an object goes from number 3 to number 1. What would happen to its centripetal acceleration? So the answer is it would decrease, right? But
Yes.
I'm confused. Why does it decrease? Because at number 3, we have tension and weight acting in the same line, in the same direction. So the centripetal force is equal to the weight plus the tension, right? And since there's a
Mhm.
greater centripetal force, wouldn't the acceleration be greater than at number?
So this one. So you're talking about you're asking this question with respect to this equation, right?
Yes.
So you're telling me that, but here's the thing: the tension itself is less. So the reason you can't really use this equation to defend your case or defend your argument is because if I compare these two equations, you can tell me, uh, well, I have the sum of both these variables in position one, and I have the difference between these two variables in position two. So
Yes.
isn't it that the centripetal force over here should be more? Well, the thing is, the values are not same. These values are not same. Those are very, very different. Only mg is same over there. Except for mg, nothing is same. Your
Oh,
tension
all
is
right.
different,
The tension is not
which
constant.
is why, yeah, it's not constant. Which is why defending your case with that argument is a bit difficult, right? So how do you then prove? Like how does it make sense? You have to talk about the velocity. What is FC, centripetal force? mv squared by r. So if you can, prove that okay, my velocity at this position is less, right? Velocity of the bob is less. Hence, the centripetal force should also be less. So that is the way to prove the argument. Okay,
All right.
right. So you have to talk about the velocity. If you're talking about variation in the centripetal force, you have to talk about the velocity.
And is
And
there a
yes, as you
reason
move
as
from, yeah, go ahead.
is there a reason as to why the speed decreases or increases either than gravity? It's just because of gravity, right?
Yeah, it's because of the way the direction of the forces are. So till this point, what we did is we analyzed the forces, right?
Yeah.
So as we saw in the topmost position, we have both the forces in the same direction. So what that causes is the tension is now going to be less. So ultimately, what happens is that variation in tension is causing a bit of difference, right? So when you're pulling it, and I will show to you guys this part. This is the part where the proof of velocity comes in. The proof of minimum velocity comes in. Whenever you have the tension varying around, that is going to cause the velocity to be different, or vice versa. You can say the opposite as well. If my velocity is changing all around, my tension is going to change. And if my tension is changing all around, my velocity will change. Why is it that in case of horizontal circular motion, we don't see anything such as this? Because tension remains constant. Nothing is changing across the journey. But in case of this, the direction of forces are changing. Once both of them are in one direction, the other, they're in opposite direction. And that causes a change in tension, right? So that is why you have change in velocity. That is why you have change in centripetal force. Are you getting the point?
Yeah.
I mean, if you confuse it, rightfully so. But what I would recommend you do is work with the formula. And when you work with, let's say, a question where they also give you numbers, right? If they also give you numbers, it will get easier to understand because you'll see right now with, as you mentioned with this formula, just by seeing these variables, it is very hard to grasp as to what is my centripetal force in
Yeah.
this position. It is mv squared over here, it's mv squared over here as well. I don't understand what's happening, man. So when you work with numbers, then it becomes easier to understand. Okay, this is why, since tension is so little over here, my centripetal force is less, right?
Okay, so I was just wondering why does the speed decrease from 3 to 1? Is that because of gravity only?
So my answer, I mean, yes, gravity. Underlying reason is gravity, but Why gravity? Gravity because the direction of the forces are changing. So the mg and t1 over here acts in this one direction, and over here they act in opposite direction. That is the reason. So
Yeah.
sure, gravity, but like what's happening is the direction of the forces are changing. That is why, right?
All right.
So it's a bit of I'm thinking how else to put it, but it's just that when you think of it, I'll keep getting back to the tension bit, honestly. But when you think about the tension, how the tension is changing, I guess it will start making a bit more sense. Uh, and working with numbers. Otherwise, does speed have anything? Yeah. So this again, centripetal force. If your speed is greater, then centripetal force is greater. So acceleration is v squared by r. Yeah. So if your speed is greater, your acceleration is also greater. Both are very closely related. Yes. So ultimately, coming to the last part is, how do I prove to you guys or show to you guys what is my minimum velocity required for the circular motion to be carried on, right? What is that minimum velocity? How do I find that minimum velocity? So before I get into that, you guys know what position I should analyze, and that is the topmost position, right? The topmost position is where we will have the string going slack. So that is what I should analyze to find what should be the minimum velocity. Okay, so if that's the case, let's analyze position one. Now, over here, how do I find the minimum velocity? First, let's work with the force formula. What's my force equation? There's an F net, which is downwards. There is weight mg downward, and there is tension, which is also downward. So everything is downward, great, all positive. Now, for my velocity to be minimum, what should be the case? For the velocity to be minimum, my string should be almost slack. So what happens if the string is slack over here? It is the center and this goes around. If the string is slack, if the string is slack, it will not complete this entire oscillation. It will just fall down. It will do what? It will just fall down. So if it doesn't have enough velocity to keep the string tight, in that case, the ball doesn't complete the entire circle. Very simple. So what do we want? We want to make sure to find the minimum, absolute minimum velocity. We want to make sure the string is almost slack. Now, if it is any more than that velocity, the string will remain tight. So to find the minimum, what do? I want to make sure tension is momentarily zero. Momentarily zero. That is what I find. At what velocity is tension in this position, in this exact position, that is position one, momentarily zero. That is what I find out. And that is also what I equate. So if this is my equation for this position, what I'm going to do is I'm going to say, well, T1 should be zero momentarily at this exact position. If I do that, I'm going to say my net force, Fc, is going to be exactly equal to mg. And if that is the case, then if I break Fc down into mv squared by r equate to mg, what I'm left with is v squared by r is equals to g. If I make v the subject again, v is equals to root over rg. So this, my friend, is the minimum velocity you need for any object to remain in vertical circular motion. And what does the minimum velocity depend on? The radius of the vertical circle and the gravity, not mass. So this is telling you that this entire motion is is mass independent. Doesn't matter. You can have 1,000 kg of an object over here. Will not matter as long as you can put it at a velocity equal to this, it will go through vertical circular motion. It does not matter. Mass does not matter, right? Because do you have mass over here? No. So it can be, anyway, it doesn't really matter. So for the minimum velocity, what do we need? The radius and the gravity. That's how you find it out. Are we clear on that? This is the formula for the minimum velocity. Okay. So what are the key takeaways over here? When you have too less of a speed, my object will not complete the entire circle. Okay. It will probably, let's say, if it's going around like this, it will start off over here, go around, and just fall down. And if it has enough speed, it will go on, and go on. It will keep going through that vertical circular motion because it has the right speed throughout the journey. Right? Right? And if you have too much speed, the only problem we have is the string can break off. Nothing else. Nothing else. And that's pretty much it. So this formula, you can see the star, decently important. They may ask you, what is the minimum speed for the object to remain in vertical circular motion? And this is what you're going to use to answer. And all of this is basically the proof. All of this is basically the proof of everything we did. And we did everything in steps to show you guys how we come to the minimum velocity bit. Okay? And this is mostly just concept building, nothing else. Ultimately, you'll just need this formula or a few upstairs. That is, the horizontal circular motion and all that. Otherwise, there's not much over here. Right? Do we have any question till this point? Anything that is sort of bugging you, is not making sense till this point? Okay. 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 Fair enough. So now, contact forces. This is the last thing of circular motion, and then we will start off with gravitational field. So with contact forces, again, I come back to that same example, which I have probably said till now like 5 times. Where's the best example? Because most people relate to that example. You have a cup of water, right? You have a cup of water, and you attach a string, right? You attach a string. There's a person holding it. I don't know what I'm drawing, but there's a person holding it, and you put this around to vertical circular motion. Okay. So you're trying to rotate this cup of water around into a vertical circular motion. And what you're trying to do is you're trying to move it at a certain speed such that this water does not spill out. That is what you want to do. Great. So, what are the things we do to find that speed? Now, what you will realize is ultimately, it comes to the same equation. But more than that, I just want to go through this entire derivation bit with you guys. So, regardless of what we come to, I just want to show to you guys what the thought process is of deriving it, or what the thought process is of analyzing the forces. Because the skill that you are acquiring over here through all of this, even though these questions might not come, is how do you analyze the system? How do you analyze the force? How do you formulate equation? That is the skill you need. That is the skill you need. So, anyways, coming back to over here, I'm going to model a similar experiment as this water example, where I have a container filled with noodles, okay, and that is being rotated around in a vertical circle. Great. So again, over here, let's analyze the bit of noodles, right? Because that is what I'm worried about. Because I don't want that to fall out of the bucket, sorry, the container. And that is essentially the main part of this conversation. How to make sure that doesn't fall off? I don't want my noodles to fall off. So I'll be analyzing the forces on this orange thingy, noodles, right? So now for that, what are the forces acting on it? A, there is the weight, mg, this my friend. What else do we have? There's a contact force, and very, very importantly so. It's going to be very important for us to understand what's happening over here. So what contact force, you ask? So if this noodles is pasted, or not pasted, but like is pressed against the bottom of the container, there must be a contact force or a normal reaction force. If you stand up, obviously you feel a force the floor applies on you because you're standing. You're applying a force on the floor, hence the floor applies a force on you. Why do you feel weightless when you fall down? Why do you feel weightless when you fall down? Because there's nothing giving you a reaction force. Hence, you feel weightless. But when the moment you land, you again feel some amount of weight that is exactly equal to your body because the floor applies a reaction force on you, a contact force, normal reaction force, right? And you all may already know that. So, similarly, over here, if the two bodies are in contact, noodles and the container, there's a normal reaction force. So essentially, I have two main forces acting on my noodles. Okay. So one is the weight, mg, the other is normal reaction force. Now, interestingly, so over here as well, in the topmost position, both the forces are acting downward. So see how it's similar to my previous case scenarios that we talked about today. It's very similar to that, right? So since that's the case, rightfully so, we will also come to a similar equation. But anyways, let's do it again and see what happens. So the net force on my noodles is going to be what? The weight of itself, mg, plus what? Normal reaction force, n. What is this normal reaction force, my friend? The force that the container applies on the noodles. Okay? The red arrow. Now, if that's the case, I can say the FC net force is equals to the sum of the weight and the normal reaction force. Now, finally, if I make normal reaction force the subject, then what I have is centripetal force, right, minus the mg is equals to my normal reaction force. Now, this equation is important. I've basically broken down the centripetal force into mv squared by r. Now, this equation is very important. Why? The reason this equation is important is this tells us when is the normal reaction force 0 and when is normal reaction force not 0. Because when the normal reaction force is 0, the noodles will plop out. It will just fall down because there's zero contact between the bottom of the container and the noodles. So what my normal reaction force is telling me is there's contact between noodles and the container. And if there's contact, that means the noodles is being pushed down to the bottom of the container. And if there is no contact force, that just means the noodles will fall down. The noodles will what? Fall down. Right? So this equation, that's why it's very important. Let's see why it's important. Let's do two things. What will we do? We'll do two things. One is I will increase the velocity or I will decrease the velocity. If I increase the velocity, what happens? If I increase the velocity over here, what's going to happen is my centripetal force increases. And if my centripetal force increases, my normal reaction force also increases. So the contact force between noodles and the container increases. Hence, less chance that the noodles will fall down. Agreed? And this is what our intuitive side should tell us as well. Our physics intuition should also say the same thing because we discovered the same thing above. When working with when working with the tension thing, it was the same idea, exactly same as over here. When we increase the velocity, tension increases. Same over here. When you increase the velocity, your normal reaction force increases. What happens if I decrease the velocity? Centripetal force decreases. Great. Hence, my normal reaction force also decreases. And this normal reaction force will decrease until it is zero, and then finally the noodles will fall out. So how do you find the minimum velocity? Same thing. You say my normal reaction force is zero. There's Fc and there's mg, and you equate Fc is equals to mg, and what you get is V is equals to root rg. The same equation you get. Same equation, right? So it's the same thing, essentially. And if I do it again with this position, what happens over here? What happens over here? Again, with our tension case, a similar case scenario, mg is acting downwards. That is on my, what do you call it, noodles, and there's normal reaction force. And which direction is my normal reaction force? Upwards, right? The normal reaction force is upwards. So the force by the container on the noodles is upwards. So now if I write down all the forces on my piece of noodle, I say the F net force on the noodles is normal reaction force that is upwards minus mg. And this F net points upwards. Great. I do the same thing again, and I say I make normal reaction force the subject. Ultimately, I get normal reaction force is equals to the sum of centripetal force and mg. And this, very similar to your previous case scenario, also shows, okay, over here, while this is the difference between both the forces, this is the sum of both the forces. So in case 2, where it's in the bottom position, it is the sum of both the forces. And in case 1, it is the difference between both. So very similarly again, at the bottommost position, obviously the noodles won't fall out. It won't. Why? Because maximum normal reaction force. So over here, N2 is greater than N1. So if you had a hard time with understanding the previous case, that is a tension one, you can think of this one rather to get that intuition. That why is it at the topmost position we have, the string being slack or normal reaction force being less? Because this probably, whenever I teach, I start off with this surely, but because it's pretty much how you're supposed to. This is what may come in your paper, and you can do a lot of maths with it with the tension. But whenever I go to this part, this somehow makes more sense to a lot of students because they can imagine the noodles falling out. They can see the problem with the normal reaction force being zero, and they can fathom that better for some reason because it's more intuitive to think of. So then they go like, okay, well, makes sense now. But whatever works for you, I've laid both the examples out for you, and I've explained to an extent that how the forces change, how the velocities can be determined, what is the minimum velocity, right? And how the normal reaction force of the tension is varying through the journey. Okay, so you can take screenshots, whatever you want to do, and there are problems as well regarding this, problems as in questions that you can solve. This is a question that you can take a screenshot of and try and solve for yourself. It's probably from the book, so you can take a screenshot. The answer is yeah, you could try. Okay. So try this. Um, Other than that, these are the two questions that I had given you guys. If you guys have any question with these two, you can let me know. But right now, I'll be eager to move into gravitational field. And before that, if you guys have any question, let me know. So we're done with circular motion. Officially, we're done with circular motion. There's nothing left. Literally, there's nothing that is possible for it to be left in circular motion. Anything that can be covered, I've covered. Okay. So any question till this point, we've taken 2.5 classes for circular motion. Any question till this point for circular motion? No? Is my screen visible? I'm hoping so. Well, yeah. Okay, great. So I'm guessing no question from circular motion. Do you guys need a break, or should I move on to gravitational field?
We can continue.
Yeah. Okay. So that is motion in circle. What is next? Gravitational field. So this is gravitational field. One of my what happened? Yeah. This is a very interesting topic again. Love this topic. So a bit of background, let's say. So this topic, as you do study it, the reason I find it interesting is it gives you the tools to work with space physics. So it gives you the tools to work with, let's say, stuff like orbital mechanics or astrodynamics. You start understanding how things in the space work. So that's why I find it to be at least quite interesting. And before we get into any of that, the first thing I will do is what is gravitational field? If this is a topic name or gravitation, you can see it written as gravitation as well. That's also possible. But essentially, what is gravitational field? So you need to understand what fields are, right? Fields, in essence, all it means is it's a region of space. You can write it down as well. A field is a region of space where a force is felt. Now, why is that force being felt? Felt? Who is causing it? Depends on what kind of field we're talking about. But in general, fields, it just means it's a region of space where a force can be felt. As simple as that. No complication. Now, when we specifically want to talk about gravitational field, things are way more specific, right? Now, in case of gravitational field, what happens is that field, that force felt on any object in any space is due to the mass of any object or some object. So if there is any random object over here, doesn't matter what it is. It's a charge, it's just a mass, it's a magnet, doesn't matter. If it has mass m, it will have something called a gravitational field. It will have a pull force. It will have a what? A pull force. It will have a tendency to pull things or objects towards itself. So this region of space, wait a minute. This region of space that it just created, that will yield technically with respect to maths will yield to infinity, but as it grows bigger, as we cover larger space, the field strength decreases. But near its surface or near its body, the field is very strong. Okay? So the field is very strong near the body. Or the force felt near the body is very strong. What I really mean, what I'm trying to do, by the way, right now, I'm not teaching you anything. I'm giving you something called intuition. I'm trying to give you guys a bit of intuition of what it is, what you're going to be working with. So I'm trying to ease you guys into the topic, right? So when you have this object and I have myself walking in, right now I feel very little force. But as I grow closer to the object, it feels like the object is sucking me in. The exact same thing happens with Earth. Or let's say black hole. Why does black hole suck things in? Why do we say that? Because it's a really, really heavy object. Mass. It's a really heavy mass. So as you tread towards a black hole, you get sucked in. That's the reason. Really heavy. Same with any object. It's just that the magnitude of that field is less or more. But the field always exists. If you have a pen in your hand, it has a gravitational field. It has a field due to its mass. And you have to believe that and understand that. So that's a simple part, right? What is a gravitational field? It is a field caused by any object's mass. Okay? Okay? Right? So, how do we formulate that idea and put it into words, scientific words, and write a definition? This. A gravitational field is a region of space where a mass experiences a force due to the gravitational attraction of another mass. A lot of words, but let's break it down. Coming to that same example where I had this small object and I was walking towards it. So this small object has this pull force, which is, pulling objects in towards itself. And I was, let's say, walking towards this body, this piece of mass, and I feel like I'm getting sucked in. So what's happening over here? What is happening over here is there's an attraction between this object and me. Mind you, even though I'm a much smaller being or an object, I'm a much smaller object compared to this larger object, I also have gravitational field. Don't think that I don't have it. I have it in me. I have the gravitational field. Both of us, this object and me, have a gravitational field. Now, this field is also a gravitational field. This field is also a gravitational field, right? Now, when both of these objects interact, only then do you feel the effect of the gravitational field. If I didn't exist, I wouldn't know where the gravitational field is or how the gravitational field is felt. That force is only felt when there's an attraction between two objects. So as I proceed towards this object or I remain over here, there's an attraction between us. There's an attraction between us. This object is pulling me towards itself, and I, with the mighty strength I have, I am pulling the object towards me as well. This attraction between us is the force. Why is this attraction taking place? Because both of us have a gravitational field and both of us are interacting. So coming back to the definition, what is it? It's a region of space where a mass experiences a force due to the gravitational attraction of another mass. So I, let's say, am a mass, this guy over here, I am a mass which experiences a gravitational, which feels a force due to the gravitational attraction of this mighty object, this mass, this piece of mass. So due to that gravitational field of this object, I feel a force, right? I feel a force because there's a gravitational field of this object. Now, if I was the only thing in space, there was nothing else, would I be feeling any force? Doesn't matter how big I am a black hole or a white hole, I don't care. I wouldn't feel anything. Until and unless I have another object to interact with, I feel nothing. So it is only when two objects interact, only then do you have some sort of a force. Otherwise, you don't feel a force. So you need at least two objects to have that interaction, to have that force. The fields can exist. I will exist here, no problem. My field will exist, but I won't feel a force because there is no other object for the fields to interact. It is only when the fields interact that we feel a force. Okay, that's the very conceptual bit. Now, I've done enough of easing you guys into the topic. Let's get into the chapters eventually. So, first thing I want you guys to be clear about is the type of fields we have. You will learn about magnetic fields, electric fields, and right now, gravitation fields. The main thing I want you guys to be clear on is in case of gravitational field, the direction of the force or direction of the field is one direction. As in, it's just towards yourself, towards the body. So if I
So
have any object over here, sorry, yeah. Did anyone want to say anything? Okay. So if I have any object over here, this object will have a gravitational field that is towards itself, towards itself. Okay. Same thing with any other random object, any charge, any magnet, any box, your parents, me, all of us will have a gravitational field towards us. So we all who have a mass, which is pretty much everything, will have a gravitational field which is towards ourselves always. This direction of gravitational field is always one direction, and that is towards yourself. Hence, the force is always a pull force, pulling towards yourself, pulling towards yourself, pulling towards yourself. It's never a push force. There is no concept of repulsion in gravitational field, and you will get to understand why. You will get to understand why. So, first thing, clarifying, always a pull force. Hopefully, you guys understand that. Always a pull force. And the field lines are always inwards. If that's clear, the other thing is what happens in electric fields. You guys know in electric fields or electricity in general, there are two charges. One is a positive, one is a negative. In case of positive charges, they have an electric field which is outward. And you can say it's a push force. So if I bring in a positive charge over here, this positive charge will feel like it's being pushed away, right? It's getting pushed away. But this same positive charge I bring to a negative charge, it gets pulled in. So now it acts more like gravitational field. So whenever you have opposite forces, opposite charges, it acts more like, not more like, it acts exactly like gravitational field because it's a pull force. It's attractive. The technical word, or the right word is attractive forces. Remember that, attractive forces. But in case of repulsive forces, which is positive and positive, they're again pushed away. Pushed away. This does not happen in gravitational field. Does not happen. Okay, that you guys need to be very clear about. See, it is only in electric fields that you have two different types of fields. One is for positive and one is for negative. That does not happen in case of gravitational field because there's no difference between masses. There's no two type of masses there. So it's always the same. If that is clear, the other thing I want to talk to you guys about is this box that I have and how gravitational field might act for this box and what would be the effect of it. So let's say this is your surface. So this is Earth, and I have a box over there somewhere out on top. And on that box, what we have is something called weight acting, right? And due to that weight, the box wants to fall down. Why is that weight acting? Because gravity, gravitational field. And what is gravitational field? Where is the gravitational field coming from? Earth's mass. So Earth is so damn massive, it has a really, really strong gravitational field. And that ultimately causes the box to feel a weight, right? So due to the gravitational field of Earth, the box has a weight, W, pointing towards the center of Earth. And you will see all of this in much more detail eventually. But the other thing I want you guys to notice is the field line. And if you guys don't know, what I want you guys to look at is this white line. What is this? This is the field line, or the direction of gravitational field. Now, near the Earth's surface, this field line is actually straight or parallel to each other. Why? Because due to the Earth being so damn massive, that near the Earth's surface, you see the curvature of Earth as pretty much zero. When you walk down on the street, do you see the Earth bending? No, you don't. You don't. You see the road as being as straight as possible. So, since the Earth is so massive, when you're on the surface with the stature that we have, meaning for how small we are, we can't make out the curvature of Earth. It is only when you, for example, fly on an airplane, or say you go out on space, that you can really make out the curvature of Earth with your naked eye. So near the Earth's surface, the field lines are almost straight. It seems like straight. They're technically not straight, they're technically a bit bent, but it doesn't make a difference. And what do I mean by bent, by the way? What do I mean by bent? So if I look at Earth from outer space, so if this is my Earth, if this is my Earth over here, why? Goodness gracious. So if this is my Earth and I have the field lines, how do the field lines look like? The field lines always travel through the center of the Earth, always through the center of the Earth. And you will see why. So notice something. These are the field lines, right? So now look,
Sir,
these field lines are pointing what? Yeah, go ahead.
would you explain again why is it always going to be towards the mass, the field lines?
Yes, in case of gravitational field, the force or the field line will always be towards the mass, towards the center of the mass.
And why is that again?
Which one? Towards the center or towards the
Yeah,
mass?
why is it always towards the mass?
So why is it towards the mass? That's, I mean, I can simply attribute that to how nature is. So whenever you have a mass, it's innate nature to pull things towards itself. So if you have, completely vacuum space, there's nothing in this universe, and you have two objects, two small objects, let's say two pen, right? Two pieces of pen in space. What you will observe is the two pieces of pen will eventually glide towards each other and accelerate towards each other as it moves towards itself. So the innate nature of mass is to pull things towards itself. If something has mass, it will have the ability to move things towards itself. The reason you don't see it happening, for example, if you have two pieces of pen on your desk, they won't move towards itself because there are other forces in this universe. And in case of us, we are living on Earth, and that is the biggest gravitational field, which sort of nullifies a lot of other effects, right? So ultimately, if you have completely vacuum, a completely empty space, you will be able to see the effect of gravitational field for anything, for any object, no matter how small it is. But why do masses attract things towards itself? That I don't know. No one knows. It's just the innate nature of an object to do that, right? Do we get that? Yeah. So answer is I don't know. No one knows. So why does mass attract things towards itself? Nobody really knows. but it just does that. It just does that. So yeah, and in case of positive charges, it can be repulsive and attractive. Even that, why, the true why, no one knows. But it's just that you can just say, yeah, it's a repulsive force. But why is it repulsive? Why is it that positive charges the way they are? You can ask a lot of questions. You can get into those layers, but ultimately, at some point, you will be done with the reasoning, and you'll be like, it is what it is. It's nature. It is what it is. But that's where research also happens. Anyways, coming back to our topic. So ultimately, what we have, if I come back to over here, is we have a mass and it has attraction, in the sense it has attractive forces, or since it exists, yeah, and it has a mass, it will have a tendency to have a force towards itself, which is described by the white lines. So it will have a force towards itself. It will have its own gravitational field. Okay. So now what I wanted to show you guys is, when I draw these big field lines, what do you notice? Are these field lines parallel? Are they parallel, or are they sort of moving away from each other? So these field lines are moving away from each other. As you extend the field lines, what's happening? The distance between the field lines are what? Increasing or decreasing? Increasing. So that is what I want to show you guys. So as you move away from an object, that's why gravitational field decreases. Now, that is not the reason or answer you write on your paper. I will get into the maths and derivation, those you write on paper. This is what I'm trying to put in the intuition within you guys. I'm just showing the diagrams and showing what really happens. What do you expect to see, right? What is logical over here? That's all I'm doing right now. But yeah, coming back, so the field lines, when you draw it with respect to how big Earth is, then you see that these field lines are radial and are radially inwards. So what does radial mean, by the way? Radial basically means whenever you have a line that is perpendicular to the surface of a circle and passes through the center, right? So it's perpendicular to the surface and passes through the center. If it's perpendicular to the surface, it will definitely pass through the center anyways. That's just a geometric property. But yes, so radial basically means it's perpendicular to the surface. That is all it means. So when you have a bunch of radial lines, and field lines are always radial, okay? Keep that in mind. Field lines are always radial. What it means is, what is this? What it really means is you won't ever have field lines coming in like this. For example, like this. This is not radial. This makes a theta with the surface. This is not radial. And it does not go through the center of the circle. Does this line, this pink line, go through the center of the circle? No. This is not a radial line. This is not a field line. That is not a field line. Okay, that's wrong. It is always supposed to go through the center. And they will ask you repeat it. It's a very common question to draw field lines. You guys should be able to do it. So yes, the point is over here, whenever we see from the POV of Earth for how big it is, we see radial lines. But now zoom in over here, and when you really look over here, right, and you draw a bunch of, let's say, a bunch of lines over here, horrible line. So when you draw a bunch of line over here, so there are like countless lines, field lines, right? And when you do that, when you see the difference between these two lines, so if I take a very small point, very small position on the surface of Earth, the field lines almost seem like they're close together or almost straight or parallel. So when you zoom into Earth or just look at yourself, look at things around you, they all seem like they're on level, they're straight. The surface is not bent, the roads are not bent. So that essentially means that the field lines near the Earth's surface is parallel. Is what? Parallel. Now, when you extend these lines beyond the Earth's surface or Earth's atmosphere, what happens is you see that these field lines will be radial as well. It's just that when we, with our naked eye, for how small we are, and see the area right in front of us, the field lines to us will seem almost parallel. They seem like they're almost parallel, which is why near the Earth's surface, we say gravitational field strength is almost constant because there's very little variation. Near the Earth's surface, there's very little variation. Near the Earth's surface, again, we don't see the Earth's arc. We don't see much of a difference between the field lines. So essentially, near the Earth's surface, we assume gravity to be constant up till a certain altitude, that is, beyond which we see, okay, gravity is changing significantly. Because due to this radial field line, you will see gravity. So as you move further away from Earth, you see the difference in gravitational field strength. But when you're right near the Earth's surface and you're saying, okay, I just want to move up and down by 10 meters, the gravitational field strength is pretty much the same. It's not going to change between 10 meters, right? So near the Earth's surface, we consider what? This is important. This part is important. That near the Earth's surface, we consider gravitational field strength to be constant. What do we consider? Gravitational field strength to be constant, right? And we consider the field lines to be parallel. Okay, so this spacing between the field lines is essentially what's giving away how strong the field lines are. So if you have field lines which are like this, what does this mean? Way stronger of a gravitational field strength. When you have field lines that look like this near the Earth's surface, that means gravitational field strength is weak. The field lines are spread apart, not concentrated. So those are the few things over here. Those are the few things over here. We'll talk about these again, but I just want to give you guys a heads up over here. Right? So what did we talk about? There's a difference in types of field. We have electric fields where we have repulsive and attractive forces. But in case of gravitational field, due to the innate nature of mass, we only have attractive forces. So a pull force. And we explored that field line with respect to Earth. And what we saw essentially is near the Earth's surface, the field lines, we can approximate it to be almost parallel. And that is why we consider G to be 9.81 near the Earth's surface. And that is also why you will notice when people go really high up in the atmosphere, the value of G will be different, will be different. That is also why, again, there's a difference in gravitational field strength between the North Pole and the equator, because the shape of Earth is a bit interesting. And I will talk about those as well. I'll talk about those as well, right? So there's so much to work with over here when we are talking about gravitational fields. But those are the few pointers, right? Now, this is the important part. If anything, in this class, what I want you guys to go with is this idea of law of gravitation or the formula of gravitation. This is what ultimately from this class I just want you guys to take away. What is the Newton's law of gravitation? This is going to tell you how to find out the force, that gravitational field strength between two objects. So there's something called gravitational field strength for which you don't need to consider another mass. So it's just the field strength of the object. So if I have this object over here, right, and it has a field, when I say gravitational field strength, all I need to know is the mass of this object and radius and what distance I'm considering. So what is the gravitational field strength at this distance? What is the gravitational field strength at this distance? So when I'm talking about just the field strength, I don't need like another object. All I need is this object. And then what I will test is how strong is the gravitational field of this object. So I just need a few things, a few information about this object. And that's all I need. But that is the gravitational field strength. Strength. That is not force. That is the field strength. And it's very different to what the force is. Field strength basically tells you how much force is exerted per unit of mass. And we will again discuss all of these in depth. I'm just giving you guys a bit of a heads up. Now, in case of force, what that means is the force is a net amount of force acting on any object. So when you find out using this formula, that gives you the net force on any object due to the gravitational field. So what this will tell you is if I have this earth over here, how much force is being exerted on this small mass over here at this specific distance. That is what the Newton's law of gravitation will tell you. Not how strong the gravitational field of earth is, but what is the net force on this object. And we will see that in details. We will see that in details. So now, law of gravitation. This formula you guys need to know. Absolutely need to know. So the law of gravitation tells you the gravitational force between two point masses is proportional to the product of the masses and inversely proportional to the square of their separation. So if I have two objects over here, one mass m1 and the other mass m2, what is the net force between these two? And if you guys know by now, if you guys have studied by now, whatever force m2 exerts on m1 should be the exact same for what force m1 exerts on m2. So this force by m2 on m1 and this force by m1 on m2 should be exactly equal. Newton's pair forces, right? So the forces should always be equal. And granted the force is always equal, right? Granted the force is always equal, how do I find that force? What I need to do is I need to find the product of the mass itself. So that is m1 times m2 divided by their separation. Not just the separation, separation squared. Not just the separation, but the separation squared, right? So now, this is the proportionality. This is not the equation. So what is the equation? I will remove the proportionality sign and I will include f is equals to an equals to sign and I'll bring in a constant. So the constant is going to be called g. And you guys will ask me, where did this g come from? Or where did this equation itself come from? How is it derived? The, the entire point of this equation is this is not derived. I mean, this was experimentally found out, but this proportionality was not derived. This was experimentally found out. So basically, they carried out lab experiment where they found out the difference in forces and they plotted it out. And from that, they found out, okay, these are the variables that matter. So the mass of the objects matter, and how far I put out the object, that also matters. So these are the two variables that are important to me: the mass of the object and the separation of their object. So when I'm aware of their mass and their separation, I can predict or find out the force between the two objects attracting or interacting. Right? So this was experimentally found out. There's no derivation for it. If there was, I would obviously show it to you guys. Okay? And how did they find out the G? They just plotted a bunch of forces and mm by r square. So they plotted this, and they found out g from the gradient of the curve, from the line. So you must have done similar experiments at some point in your AS, either in AS, or you will also do something like this in your paper 5 as well, at some point. So yeah, essentially speaking, this is experimentally found out. Okay, there's not much of a derivation to it. So the value of g, you'll find it later on as well, but it's probably 6.67 into the power or something. So that is a constant, and that was experimentally found out. And rest of the relation, that is product of mass divided by r square, it was found out simply by checking what matters. So they varied the mass, and so does the force change? Yeah, it changes. If I change this mass, does the force change? Yeah, it changes. If I change the distance between them, does it change? Yeah, it changes. So that's how they found out. Okay, that's the origin of the formula. So take this formula, write it down, because this is very, very important. And this is going to be sort of the bane of the rest of the um, anything that we do, any calculation we do. This will be very important. And now the distance, the separation, my friend, over here that you have r between two objects is the separation from the center of the object. And we're always going to be working with spherical objects and perfect spheres for that case. We're not going to be working with we're not going to be working with, for example, square or rectangles. We'll be working with perfect circular objects. And in that case, what we can assume is the distance should always be measured from the center of the object. So you don't measure the distance from this surface to this surface. That is wrong. If you do that, that is completely, completely wrong. What you do is you measure the distance from the center of the circle to the other center of the circle. That's how you measure the separation. Okay, so that is R, and that is an important pointer. Why? I will discuss that again in the next class, because that is where we talk about point mass approximation, we talk about Kepler's law, we talk about how we find the velocity, how we find out geostationary orbits, a lot of very interesting things, right? So till this point, all we talked about is an introduction to gravitational field and the law of gravitation. That is essentially all we covered over here in terms of gravitational field. And that is pretty much the end of today's class. Do you guys have any question for anything till this point?